Welcome back, everybody. So we're moving on to tutorial 10 of our Learning to Use GeoGebra series. And so today we're going to look at the superposition of sine waves. So in order to be able to play around with our sine waves, we want to create sliders. So let's start off by creating 3 sliders. Call the first one A sub 1 for the amplitude of our first sine wave. The next slider we'll call omega sub 1 for the frequency of our first sine wave. So we get the omega by going in this, clicking on this box with the little alpha gives us some special characters, including the Greek symbols. So we'll call that omega sub 1. And let's change that one from 0 to 10 for the min to the max. And then we'll create one more slider, and we'll call it phi sub 1 for the phase shift of our first sine wave. Okay, so now in the input bar, we'll go ahead and enter our sine wave. Call it G sub x. And that'll be A sub 1 sine omega sub 1 x times x plus phi sub 1. Okay, and that'll give us our first sine wave. Now let's go ahead and create 3 new sliders for our second sine wave. We'll call those A sub 2 omega sub 2 and we'll go ahead again, change that from to 0 to 10. And we'll make phi sub 2. We'll enter our second sine wave in the input bar, and we'll call that h sub x equals A sub 2 sine omega sub 2 x plus phi sub 2. And press enter. Okay, and then we will, in order to study the superposition, we'll get the sum of those two waves. We'll call it sum sub x equals g of x plus h sub x. And that'll give us the sum of the two waves. And so now what we want to do is we want to change the object properties a bit, so get some different colors for the different waves so we can see the differences between them. So we'll color the first one blue, and maybe we'll make it a little bit thicker, make it 3. Okay, and we'll color the second wave green. We'll also make that one a little bit thicker. And then the sum we'll color red. And we'll make that one even thicker. Okay, so then let's go ahead and also color the sliders to match up with their corresponding sine wave colors. Okay, so we'll do the same for sine wave 2. Okay, so now we've got our two sine waves, and we've got the resulting wave in red, so we can start playing around. So let's first off, let's just set the phase term to 0. The amplitude is 1 in each case, and the omegas in each case are 1, or the frequencies. So let's just look first of all at the impact of changing the amplitude. So let's make the amplitude for wave 1 get larger, and we can see that grows the amplitude of the sine wave. So if we were thinking in terms of physics, like a sound wave or an electromagnetic wave, changing the amplitude for a sound wave would be equivalent to changing the volume. So it would get louder as we change the amplitude. Then we can look at the impact of changing the frequency. So changing the frequency of wave 1 shortens the wavelength, and so that would be equivalent to a sound wave of changing the pitch of the sound wave. So that would give us, each frequency would give us a slightly different pitch, and you can see the impact of the resulting wave. So a couple special cases that we can look at is, let's go ahead for wave 1, let's go ahead and fix the amplitude at 1. Let's fix its frequency, let's say 2, and its phase difference at 0. And now let's look at what happens to the resulting wave as we change the frequency of wave 2. So we can see when the frequency of wave 2 is equal to the frequency of wave 1, and they're in phase, we get constructive interference. So the two waves are going to add, and the resulting sum wave will be the sum of the two individual waves, so you'll get a higher amplitude. So when the waves are in phase, but the frequencies are different, you can see that they interfere in these cases in different ways. They don't completely reinforce one another, and they don't cancel one another. They kind of get some unusual shapes as they're kind of as we change that frequency around. And we'll take a closer look at the frequency in a second. But for now, let's put the frequencies, make them even again. So we've just seen that when they are in phase, which means their phase are equal, then they're going to reinforce each other, and this is called constructive interference. But let's look at what happens if we take the phase and we start shifting the phase of wave 2. You can see that the amplitude of the resulting wave decreases, and when the waves are exactly out of phase by 180 degrees, you can see we have complete destructive interference, and the two waves will cancel each other. So when wave 1 is forming a peak in positive, wave 2 will be forming a peak in the negative. So when you add the resulting waves, amplitudes, you'll get 0 for the resulting wave. So we can completely eliminate the resulting wave and cancel it out with destructive interference. So the waves can either constructively interfere when they're in phase, or destructively interfere when they're 180 degrees out of phase. So now let's take another look here. Actually, let's go in and change the properties of our omega, and let's change the increment by a smaller amount, so we can change the increments over much finer amounts. Let's do the same thing for omega 2. And now let's look at what happens. Let's crank the amplitudes up a little bit. We'll go 2 and 2. So let's make the amplitude of wave 1 really high, and let's go ahead and match its amplitude with our second sine wave, and now we're going to have constructive interference. So now let's go and zoom out a little bit so we can see more of our wave. And let's move it down. So now let's look at what happens as we change omega 2 slightly, so its phase is slightly different, or its frequency is slightly different from that of sine wave 1. And what you see is now you form a superposition of those two waves that actually form beats. So the beats have their own wavelength, and we can see as we continue to change omega 2, you can change the wavelength of those beats. So let's shut off the two individual waves now, and so we can see the beats a little bit more clearly. So now they form their own wavelength and frequency of the beats, and it depends on how much the two waves are offset. But the key here is that the two frequencies are close together, but they're not quite the same. And so you get that interesting effect of getting these beats. Now, as you get further and further apart, now it just kind of goes into kind of a messy superposition between the two waves. But now let's see what happens as we get omega 2, as its frequency becomes low and omega 1's frequency remains high. Continue to lower it down, and so we'll start to see another interesting effect come into play. And here it comes. So you can see what we have is we have omega 1 with its high frequency is essentially riding on omega 2 with its low frequency. So let's plot out omega 2, and you can see as its frequency becomes low, we essentially will have omega 1 riding on omega 2. And these effects are called modulation, when we essentially modulate a resulting wave by summing up with two individual waves. And you can get all kinds of interesting effects that you can play around with. So go ahead and play around with these and explore the effects of superposition with different waves and see what kind of different effects you can discover yourself. And that's the end of this tutorial, and we'll see you again next time.